CH absorption bands. Here is a table containing the different carbon-hydrogen stretching vibrations. This carbon right here is an sp carbon. This one is sp2, while this one is sp3. Now, if you take a look into this, this sp3 carbon-hydrogen stretch happens at a lower frequency, while the sp carbon-hydrogen stretch appears at a higher frequency. Now, what is the reason why the sp carbon-hydrogen stretch appears at a higher frequency? For that, we definitely have to take a look into the strength of these bonds. The strength of the carbon-hydrogen bond depends on the hybridization of the carbon. Greater the S character of the carbon where the hydrogen is connected, greater will be the strength. So this carbon, which has more S character, so this has got 50% S character, right? So this is going to be the strongest bond, while this is going to be the weakest, right? So the strongest bond will appear at a higher frequency, whereas the weakest bond will appear at a lower frequency. The best way to differentiate between sp3, sp2, sp carbon-hydrogen absorption bands is that you're going to draw a line about 3000 centimeter inverse. So if you see peaks only on the right side of 3000 centimeter inverse, then you can say that the compound doesn't have any sp2 or sp carbon-hydrogen stretch, but it only has got sp3 carbon-hydrogen stretch. For this compound, when you draw a line about 3000 centimeter inverse, you can see that there are peaks on the right side and as well as on the left side. So we can clearly see that it's going to have some sp2 carbon-hydrogen stretching vibrations, right? Because when you look into the values here, the sp2 carbon-hydrogen stretching vibrations are between 3100 to 3020, whereas for sp carbon-hydrogen stretch, it's going to be around 3300, right? So here, so this is definitely lower than the 3300. So we can take these absorption bands corresponding to the sp2 carbon-hydrogen stretch. Okay, so we are going to draw this line. So let's draw this line. Here's the line about 3000, and anything towards the right is going to correspond to the sp3 carbon-hydrogen stretch, and anything towards the left until 3200 is going to correspond to the sp2 carbon-hydrogen stretch. We do not have any sp carbon-hydrogen stretch in this molecule because we do not see any peak around 3300. Once you know that there are hydrogens connected to sp2 carbon, we need to find out whether this sp2 carbon is associated with a C double bond C in an alkene or C double bond C in a benzene. The C double bond C in an alkene is generally going to show up around 1600 centimeter inverse. Whereas the C double bond C in a benzene is going to show two peaks, one at 1600 and the other one is going to be between 1500 to 1430 centimeter inverse. So these are the two peaks that you will be seeing for benzene. So now let's take a look into this molecule. This molecule shows two different peaks, one at 1600. If you zoom up, so you can see one at 1600 and the other one at 1500. Both of these two peaks is going to correspond to the C double bond C in the benzene ring. But let's take a look into the case of alkene molecule. So this is a cyclohexene molecule where you can see there is an sp2 carbon-carbon double bond. So this carbon-carbon double bond is going to show up at 1600. But between these two, there is a clear difference. While this peak is strong and intense, this is the intensity of this is medium. So by this, you can clearly distinguish between the carbon-carbon double bond in an alkene and the carbon-carbon double bond in a benzene. The carbon-hydrogen stretching vibrations in aldehydes are going to appear as two absorption bands. Okay, here are the two absorption bands. One is going to appear around 2800 centimeter inverse, and the other one is going to be around 2700 centimeter inverse. It's generally easier to locate these two absorption bands since no other peaks are going to come around this wave number. CH bending vibrations. If a compound has sp3 carbons, we need to look around 1400 centimeter inwards to find out whether there is any methyl group present. Now let's take a look into this compound. This compound obviously has got a methyl group, right? So what we are going to do here is we are going to drop a line around 1400. Now if you see peaks on the right side of 1400, you can definitely say that there is going to be a methyl group in the molecule. This is going to correspond to the CH bending vibrations in the methyl group. But the peak on the left side of 1400 centimeter inverse is going to correspond to the other hydrogens that is associated with the other sp3 carbons other than the methyl group. So this absorption band is going to correspond for this carbon hydrogen bond. Similarly, when you take a look into this compound right here, you do have methyl group and you also have methylene group, right? So you're going to drop a line around 1400. You can see that there are peaks on the right side and as well as on the left side. So the right side is going to correspond for the carbon hydrogen bend present in the methyl group, and the one on the left side is going to correspond for this carbon hydrogen bond, right? For the methylene carbon hydrogen bond. We'll also take a look into the last compound. So here we do not have any methyl group in this molecule, right? So let's drop a line. Okay. So on the right side of 1400, we do not see any peak close by it. So the only bands that we see is on the left side. And that's going to correspond for these carbon hydrogen bending vibrations. The CH bending vibrations of hydrogen that is connected to the sp2 carbon is going to come somewhere between 1000 to 600 centimeter inverse. But these numbers can really fluctuate depending upon the number of R groups present in the molecules. Also, these numbers can go out of range if there is a very strong electron withdrawing or electron donating group attached to the molecule.